In this video, we're going to take just a brief look at some key properties of the PDF and the CDF as previously defined. Remember that your PDF is the probability distribution function, and the CDF is the cumulative distribution function. So we're going to look at just a few properties of both of these, and particularly if you refer back to those graphs that we established in a previous video, then you'll see why a lot of these properties make sense. In addition to that, the properties of these functions, since they give us probabilities, even though they're different types, they still have to adhere to the axioms of probability. So let's start with the PDF, also known as the PMF, right? So for a discrete random variable, right? Let's call a random variable x. With possible values. Now remember, again, with a discrete random variable, it can be finite or countably infinite. So let's go for the countably infinite case, right? So let's say the values are like x1, x2, x3, dot, 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 and so on. But again, these are isolated, distinct values that have gaps between them. That's what distinguishes a discrete from a continuous random variable, right? So let's say these are the possible values of x, and PDF and a PDF given by, now remember, we had said that your PDF gives these probabilities. The probability that your random variable takes on a specific number, like an exact probability, right? And we had said that sometimes, just so that it looks more like our typical function notation, we might use a lowercase f to represent this, right? And you'll still have your x sub I in there, right? So again, let's quickly recap. We have a random variable x. It has these possible values, and then it has a PDF that we're just using this kind of generic notation for, right? And then, so the following properties must be satisfied by this function, right? So the following properties must be satisfied by f, right? And the first one is this. F always has to be positive, right? So f of xi must be greater than or equal to 0, right? So like thinking back to our previous video when we indicated or we described the PDF in the form of a table, what it's saying is, in the row of the table that has these function values, which represent these probabilities, we can't have any negative numbers. And that's consistent with our axiom of probabilities, right? So probabilities are always positive. The second property, and there are just two. Now, the thing is, it can't just be any old function that's positive. Because remember, our first axiom of probability says that the probability of the sample space is equal to 1. So what this means is, if I were to sum up all of these probabilities, right? Whether it's a finite sum or an infinite sum, which would be like an infinite series, which regardless, if I do like over all xi and I sum up these probabilities, I must get a value of 1, right? So this is, again, from our axioms of probability, right? And these are the two main properties of the PDF. So for instance, and I'll just do an example of one of these probability line charts. I won't do the histogram; those take a little bit longer. But again, let's say that here are the possible values of x, dot, dot, dot. And we know that the probability line chart, it gives these vertical lines, and the length of these vertical lines are the probabilities, right? And then it could possibly go on. So basically, again, what these two properties are saying is that the vertical lines line segments are always going to be in this either first or second quadrant. Let's say your x values could possibly be negative, and you could have some of those vertical lines on this side as well. But they would always reflect positive probabilities. So they would always be above the horizontal axis, like on or above, right? So that's the first property. The second property is now, if I add up all the lengths, because remember, each length represents a probability, which is reflected on the vertical axis here. If I add up all these lengths, they have to be equal to 1, right? So when you kind of look at these properties, they make complete sense, and there is no contradiction with our axioms, all right? So now let's take a look at the CDF, right? Now, for the CDF, what I'm going to do is I'm going to start with the graph of the CDF, and then from the graph, just kind of make some important observations about the CDF, this specific type of function, right? So it's the same setup, a random variable x with these possible distinct kind of isolated points, again with gaps between them. But the difference is now we're going to talk about the cumulative distribution function. So again, let me just remind you what it is. So the CDF of x, and it's given by, so now the difference again between the CDF and the PDF is that the CDF tells you the probability that your random variable is less than or equal to some number, right? And what we use, when we switch to the F notation, we use the uppercase F to indicate the CDF. So it will look like this, right? So that's the function whose properties we're going to talk about right now, right? But before we list the properties, let me again sketch what it looks like. And this one is kind of it's the less intuitive type of sketch, simply because we don't use a lot of these kinds of functions in like, basic algebra, college algebra, trig, calc, that type of thing. But what I will do is just list and say, again, this could go on forever. Now, the CDF, it always starts out, so once you're looking at values of x that are less than the smallest possible value of x, there's no probability associated there. So remember, they start out like this. So there's 0 here, And then once you get to that first possible value of x, it has a jump, and it jumps up to a certain value, right? A certain probability. And that jump right there is the probability that's associated with this specific x value. And then it stays at that value until you get to the next possible value of x, and then it accumulates some more. So remember, that cumulative process is that it keeps adding the probabilities of these possible values of x as you go further and further to the right on your number line. So then it will have another jump there, right? And again, the height of that jump corresponds to the probability that's associated with x2. And then it goes like this. And then you'll have another jump at the next possible value of x. It goes up by a certain amount, and then it goes across. And then what happens is this jumping process continues. So I'll say dot, dot, dot. However, because of this property here, that when we accumulate all the possible probabilities, we have to end up approaching 1. So at some point down here, maybe far down, who knows, depending on how many more possible values of x we have, we will have another jump that jumps up to 1, and then it stays that way forever, right? And that's your kind of generic or general graph of a CDF, right? And this is sometimes called like a step function for obvious reasons. It literally is you're climbing the stairs until you get to a height of 1, and then it plateaus indefinitely after that. All right? So that's the graph. So let's see if we can use the graph as a motivation for what's going on, right? Well, here are some properties, right? So the following are properties of our big F of xi, our CDF, right? Now, just like what we know about other probabilities, and if you look at the graph of a CDF, even though you have all these jumps, and it could be many of them, in fact, it could be infinitely many jumps, but it's always between 0, the graph is always between 0 and 1, right? Because we can't have negative probabilities, right? So that takes out anything less than 0. And because when we sum up all the probabilities, we get 1, well, that's the max. So right away, we have this pretty obvious property that these probabilities here are always between, right, 0 and 1. And this would be for all real numbers, right? All values of x, your CDF is always between 0 and 1. The other interesting thing, and that we can see, again, from this stepwise pattern, this staircase pattern going up, is that as I move to the right on my number line, so as x gets bigger and bigger, so does the probabilities, right? Because they always go up. They can't go down. The only way they could go down is if you somehow add a negative probability to this. But there is no such thing as a negative probability. So another observation is that f of xi is a non-decreasing function. Now, you might be asking yourself, why don't I just say increasing? No, increasing means that the function always goes up, which is not true because look, it's constant for a lot of these intervals. So on the intervals, right, where you have the gaps between those possible x values, it doesn't change. So it's not always going up, but what is always true is that it never goes down. There's a difference between saying that something always goes up versus saying that something never goes down, right? So our function here, our CDF, is a non-decreasing function, right? As long as you go far to the right, the further you go to the right, it eventually it will approach 1, right? In fact, that observation leads to two, and I'll state these two together, right? In fact, there are some obvious limit properties about this, right? If you take the limit as xi goes to negative infinity, right, of your CDF, eventually you will hit 0, right? It might happen here, or it might happen somewhere further to the left, but if you let your x approach negative infinity, then your CDF has to approach 0, right? So now you know we're inching closer and closer to calculus when we start talking about limits, right? Well, we're not quite there yet, but we're getting there. But yeah, all this is saying is, as you go far to the left on the graph of your CDF, that function is going to approach 0, right? When will it actually hit 0? We don't really know because that depends on the values of x in your sample space. And that's why we would have to say something like this, to say if you keep going far to the left indefinitely, then your CDF must approach 0. Similarly, if I go far to the right, right? If I go far to the right indefinitely, at some point, then your CDF is going to accumulate all the possible probabilities, which is 1. So the other limit at infinity is that as xi approaches positive infinity, then my CDF must approach 1, right? So again, just by looking at the graph and just thinking about how it's defined, we can see that a lot of these properties are I don't want to say completely intuitive, but it's certainly things that we can see from a graphical standpoint. And let me make a fourth and final property about those jumps so that we have it written down carefully, right? So the fourth property is that the PDF can be obtained from the CDF by determining the heights of the jumps, right? So little f of xi can be determined by computing the heights of the jumps on big f of xi, computing the heights of the jumps let's say in f of xi, right? So in other words, that when we're computing these jumps, we would have to take a difference, right? So I'll just say this is like the calculation that you need here is a simple difference, right? And the reason why I wanted to mention that is because when you start with little f, as we did in the previous video, and we accumulated the probabilities, we did so by addition. Now, I'm going to illustrate with a final example. If I gave you the CDF and I wanted to figure out what the PDF is, then I'd have to do so by subtraction. All right, so let's look at that example, and that will be it for this video, right? So let's look, and what I will do here is I'll give you the CDF in the form of a graph. All right, so let's say, and what I will do is, let's say 1, 2, 3, 4, 5, 6. So I'm going to draw the graph of the CDF first, right? So let's say it has a jump right there at 0, and let's say it jumps up to, let's say this is 0.2, and then it's constant all the way here, and then it jumps up to, let's say, 0.5, right? And then at 3 there's another jump. Let's say it jumps up to, say this is 0.8, and then let's say it's constant all the way to 6, at which it jumps up, and then let's say that it is 1 from there on out. So let's say this is 1.0, right? So this is a completely legitimate CDF. Just by looking at the graph, we can see that it hits every one of our properties, right? And let's use the fourth property now to determine what little f is, right? So the graph here is big F of x, right? So the first thing that you would want to identify are the possible x values for this random variable, right? So essentially you want to identify the sample space. So the sample space, and that's again, where we use the lowercase x, and I'm just going to list the possible x's. How do I know which x's are possible? Those are the values of x at which you have those jump discontinuities, right? So it's each time there's a jump, you know that the function accumulates more probabilities, right? And it does so until it gets to 1. So the smallest value of x, or the first value of x at which we have a jump, is at 0. So 0 is our first possible x. And then after that, it stays at that constant level of 0.2, right? And then there's a jump again at x equals 2, so then it jumps up to 0.5. So I know that another possible value of x, or you could literally say the next possible value of x, is 2. And again, it's constant. It's now constant here. And then at 3, there's another jump. So that's another possible value of x. And then it jumps up to 0.8. And then it's constant, 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 and then it hits 0.6. I'm sorry, not 0.6. It hits, at 6, there's another jump, and then it hits the total probability of 1. So then these are the 4 possible values of x. And it's important for you to see sample spaces like this where they're not necessarily consecutive integers. Like the gaps between them is different. We have a gap of 2 between 0 and 2. Then we have a gap of 1 between 2 and 3. Then we have a gap of 3 between 3 and 6. So it doesn't have to be uniform, right? I mean, yes, many instances we might have a random variable that can take on the consecutive integers, and maybe it never ends, in which case it would be countably infinite. but this is a random variable that whatever it represents, right? The possible values are 0, 2, 3, and 6. Okay, so that's the sample space. Now let's see if we can list the associated probabilities. So like, what is the probability that x is equal to 0? Or what is the probability that x is equal to 2 and 3 and 6, right? So let's find the associated probabilities. And the fourth property in the CDF says it's the height of every jump, right? So the jump at x equals 0 is a height. It has a height of 0.2, right? Because you're jumping from 0 up to 0.2. So I will say, okay, so let's call these the xi's, and then this will be f of xi. And then here are the associated probabilities. Well, actually, yeah, that's fine. Let's write it like this. And then what I'll do is I'll just have them correspond, and then over here on the right, I'll set it up in a formal table, right? So the jump at x equals 2 is of a height of 0.2. So this is 0.2. Then at x equals 2, the function jumps up by a jump of 0.3. It's the difference between this f of x value, big f of x value, and this one. So this jump right here, going from 0.2 to 0.5, is 0.3. And then do the same thing at 3. At 3, it jumps up from 0.5 to 0.8, and that's a difference of 0.3 again. And then finally, at the last possible value of x, there's a jump going from 0.8 to 1.0, and that difference is 0.2. So now, let's say I wanted to put this in a table like we did previously. I would have our xi's, and then here I'm using, again, little f to represent the PDF, list the possible values, right? And it's pretty standard that you only list the possible values. If you list other values of x that are not possible, then you'd have to put a probability of 0 there. Because again, remember, a 0 probability represents something that's impossible. But based on where these jumps are, we know for a fact that these are the 4 possible values, and here are the associated probabilities, right? 0.2, right? So that's how you can go from the CDF to the PDF. And if you think about it, a lot of the method is similar, for instance, in Calc 1 where you had to identify certain types of discontinuities. Well, for the CDF of discrete random variables, they're only going to have jump discontinuities. So you have to identify where there is a jump, that will tell you the x's, and then how much is the jump, that will tell you the associated probabilities, right? So hopefully this look at some of the kind of the theoretical properties behind the little f and the big F, as well as this example here, really gives you an idea of the close relationship between the two. And going forward, we will have lots of opportunities to work with both. So I know you can't wait for that. Neither can I. See you then.